Hi, in the last few sessions, we have designed Baud clock generator and serializer module for our UART project, and we have simulated them and tested them as well. Now today, we will merge these two modules to design our UART transmitter. Means we will use Baud clock generator, which will generate pulses to drive the serializer module based on very specific bit period, which is calculated from our system clock frequency and our baud rate. So in this example, we will use 50 megahertz of system clock frequency and the baud rate will be 115200. Although you can simply change them based on your design requirements because our VHDL code are flexible enough to work on any combination of baud rate and system clock frequency. So this is the structure of our UART transmitter module. You can see we have two modules here, which we have already developed. And these are Baud clock generator and the another is serializer. If you are not clear about these two modules and their VHDL codes and test benches, then please watch the previous sessions. Because in this session, we are going to interconnect these two modules. So you can see that this UART transmitter module has two input ports, and these are TX start and TX D in. TX D in is our parallel data, which we are going to transfer over the RS-232 protocol. TX underscore start is the input port, which will tell our module that when this module should load data and when it should start transmission. Means when this TX start pulse is asserted, then our input data will load into the module. And when this TX start pulse is deasserted, our module will start the transmitting data, right? Next, we have two outputs in this module. One output is our transmitting bit or transmitting data, and another output is TX ready. TX underscore ready will indicate that either our module is ready to capture any input data or not. Because if our module is busy in transmitting the data, then this output should be low, which will indicate that our module is busy in transmitting data and it cannot take any new data at this moment. And of course, we will have clock and reset ports. Now, if you look at this structure, then you can see that our TX underscore D in is connected to the D in port of our serializer. This TX underscore start is connected to the load port of this serializer. And it is also connected to the start port of our Baud clock generator. Now our output port TX underscore D out is connected to the D out port of serializer. And our TX underscore ready output is connected to the ready port of Baud clock generator. So these are our input output port mapping. But we have also few ports pending of serializer and Baud clock generator. And we will connect them by using the internal signal. So we have this TX underscore Baud clock signal, which is connected to the Baud clock output of the Baud clock generator and a shift enable input of the serializer module. So this is a very simple structure. And now we will write this into our VHDL code. So let's move. Okay, so you can see we have 4 different VHDL files here, which we have written in the previous sessions. So this one is for serializer, and we have written the test benches for this serializer in this VHDL code here, right? Then we have the another VHDL code for this Baud clock generator here. So this is the code for Baud clock generator, and we have tested this module using this Baud clock generator test bench VHDL code. Now in this session, we will combine both of these modules. So that is serializer module and another is Baud clock generator. And by using these two modules, we will design our UART transmitter. So what we will do that we will create a new file and now we will save this as a .vsd file. So click on file and then save as. Now first I will select the file type. So that is VHDL file, right? And the extension is .vsd. So select it. So this is the format, that is basic hardware description language. Select this. Now you can see that we have two testbench files listed here that we have written in our previous sessions. As we did in our previous sessions, that all of our VHDL module file are listed in the source folder, right? So we have this source folder listed here. So double click on it, and now we will save this file here at this location. So give the file name, and the file name is suppose UART TX for transmitter, right? Now click on save. Now first we will give the library declaration and then entity declaration. So for this I will use this serializer file, and then I will copy this part from here and then paste it here. So we have this library declaration here and we have this entity declaration here. So we will modify the content of this entity with our UART transmitter module, right? So we will replace this serializer with our entity name. So this is UART underscore TX. Now copy this. So UART underscore TX, and then replace this and serializer with and UART underscore TX. Now we will quickly write the architecture body as well. So architecture behave of UART underscore TX is, then begin, and in the last and architecture means and behave. Now let's define the input output port for this UART underscore transmission module. So we will need this clock input and reset input in this UART transmission module as well. So I will leave these two inputs as it is. Now let's define the other input output ports for this UART transmission module. So first is start pin. So let's give it some name. Suppose this is TX underscore start, right? So this is input type and STD underscore logic. So this is correct. Next we have this D in input, right? So let's remove this load from here for now, and we have this D in as a second input. Now let's change its name to TX underscore D in, and this is input type STD logic vector and data width -1 down to 0. Now for this top module, let's change this generic name to TX underscore data width, and I will do the same for this generic here. So this is TX underscore data width here. So this is good. Now we have another port, and that is output type. So that is D out. So let's change its name to TX underscore D out, and that is output type and STD underscore logic. Now semicolon at the last. And we have one extra output, that is transmission ready. So TX ready. So that is output type, and this is STD underscore logic, right? So these are all input output ports for this UART transmitter module. So we have this library declaration here, and we have this entity declaration here. Now this is the part for generics, and this is the part for port declaration. So at the moment we do not need this default state. So I will remove this from here, and now that looks good. So let's jump to the architecture part. So this VHDL code is actually very simple, because what we will do in this code, we will use our Baud clock generator and our serializer module as an component here, and we simply connect its port according to this UART transmission module, right? So for that, first we need to declare Baud clock generator and serializer as a component here in this UART transmission module, right? So for this, what we will do, that we will copy this Baud clock generator entity. So let's copy this. Now go back to this UART transmitter module. Now here, after this architectural declaration line and this begin keyword, we will declare both of our components. So let's paste this Baud clock generator as a component here. So replace this entity keyword with the component keyword, because this Baud clock generator is a component here, right? So this is a component, and in the last we will replace this Baud clock generator with the component keyword. Now we will do the same thing for serializer module. So we will copy this entity part of this serializer, and then we will paste it here in the declaration part of this UART transmitter module. Now again, we will copy this component keyword and I will paste it or replace this entity keyword with the component keyword. Same I will do at the AND serializer. So now this will be AND component. Now we will interconnect all of these input output ports of these two components according to the UART transmitter module, right? So for this, I will copy this whole part from here. So I will copy this and paste it in this section of architecture. So now we will give the port map and generic map for this Baud clock generator first. So update this part with port mapping and generic mapping for this Baud clock generator. So first we will give the instance name. So give it some name. For example, this is Baud clock instance, right? And this is a component of Baud clock generator. Now remove this is from the last. Now we will use keyword generic map for generic mapping and same for port map for port mapping. So this is port map. Now our data width will be same as our transmitter data width, right? So this will be our transmitter data width. So tx underscore data width, comma. Now our system clock frequency will be 50 megahertz. So this will be 50 megahertz. So 50 000 comma. And now let's give the baud rate. So this will be 115200, right? Well, this is completely fine if you're only working with this clock frequency that is 50 megahertz and this baud rate that is 115200. But if you want to make your VHDL code more flexible, which can support diversified system clock frequency and different baud rates, then we will recommend to use generics here, right? So this system clock frequency will be our transmitter system clock frequency. So this will be transmitter system clock frequency, and this baud rate will be our transmission baud rate. Okay. And now we need to define these two generics in the generic section of this code. So this is here, enter, paste. So this is transmission system clock frequency and this is integer type semicolon. And now we have the third generic, so that is tx underscore baud rate. Okay, so that is again integer type, right? Now quickly arrange them in a better way so that they can look better. Same I will do to this port declaration part as well. Okay, so this looks better now, right? Now come back to our component part. So this is our generic map, right? And now we will map our ports. So this clock will be connected to the system clock. So this will be connected to our clock, comma. Now this reset will be connected to reset. This start pin will be connected to the transmission underscore start. And now we need to connect this baud clock. So this will be connected with our baud clock, right? Although this is not an input output port for this transmission module. So this baud clock will be act as an internal signal for this transmission module. And we will define this signal sometime later. But for now, let's say that this baud clock is connected to this baud clock. Or even we can say that this baud clock is connected to transmission baud clock. And we will define this tx underscore baud clock in some time. And now we have this ready output. So this will be connected with our tx underscore ready output, right? Okay, so that's complete our component mapping. So let's move this AND component part from here and remove this semicolon from generic map. So this is our component instance for Baud clock generator. Now we will do the same for the serializer. So this is our serializer module, and now we will map its generics and ports according to this transmitter module. So first we will give some name to this. So suppose this is serializer underscore instance. This is component of serializer. Now remove this is from the last. Now write generic map. So this data width is our transmission data width, comma. Now we have this default state. Now for RS-232 protocol, we have 1 as in default state. So what I will do that I will mark it 1. Although you can also create a generic for this default state. But we know that we are working on the RS-232 protocol. And for this protocol, the default state is always 1. So this parameter is something that is not changeable for this RS-232 protocol. So there is no need to define this as a generic. So instead I have hard coded this with logical 1. Now we will give the port map. So let's remove the semicolon from here and now write port map, and now this clock signal is connected to our clock, comma, this reset is connected to the reset pin, now comma, this shift enable is connected to, now if you remember from the serializer module, then this shift enable pin is actually the pulses which was used to enable the shifting and transmitting the bits sequentially. And for the baud rate of 115200, we have generated the pulses at the time gap of 8.7 microsecond, right? So this pin is actually the bit period of baud rate. And for this module, this is shift enable pin will be connected to this TX underscore baud clock. So you can see that this baud clock generator will generate this TX underscore baud clock because this was the output port for this baud clock generator module. And now this TX underscore baud clock will drive this shift enable of serializer in this UART underscore TX module, right? Next, we have this load input, right? So what will happen that when you start your UART transmission, then your data at the input will load to the serializer, right? So for this UART transmitter module, this will happen when you apply TX underscore start pulse. So this load will be connected to our TX underscore start pin, right? Now next input is D in. So this will be connected with our TX underscore D in, and our output is connected to TX underscore D out, right? So this completes our port mapping as well. Now we have one small problem here, and that is because we have this TX underscore data width which will define the size of our input data. But this RS-232 protocol has two extra bits, that is one start bit and one stop bit, right? So we need to generate two extra pulses from the baud clock generator. So what we will do that we will move to this component section of this baud clock instance, and we will say the data width for this baud clock generator is TX underscore data width plus 2. So this TX data width is 8, means 8 bits, and then plus 2. So 1 for start bit and 1 for stop bit. So now this data width will be 10. Same way we will have 10 bits to transmitter for this serializer. So we will do the same, that data width will be our TX underscore data width plus 2, right? Now in this component mapping, we are saying that this D in is connected to the TX underscore D in, right? But this TX underscore D in is 8-bit wide because that only contains the data bits, which do not include the start bit and stop bit. So let's create another signal and let's name this TX underscore packet. And this TX underscore packet is our start bit, so which is 0 here, then our data bits which is TX underscore D in, and then concatenation with stop bit. But we have the small problem here. If you write this start bit, then data width and then stop bit, can you guess what it is? So the problem is that RS-232 protocol transmit the least significant bit first, means LSB. So in this case, this 1 is our LSB, and that is wrong, right? Because our start bit is 0. This means we need to transmit 0 first. So what we will do, that we will replace this 1 with 0. So this will be transmit first, and that is our start bit. Then it will be followed by the data bits, and in the last stop bit, which is 1. So this is the correct way of writing. Okay, so this completes the code for architecture part as well. Now we will define the necessary signals for this UART underscore transmitter module, which we have used in our architecture section. So we have this TX underscore baud clock, which we have used here. So this is a signal here. So this is a signal TX underscore baud clock. and that is std underscore logic type, right? We have another signal and that is tx underscore packet, right? And that is std underscore logic underscore vector. Now the range will depend on this data width, right? So if you are transmitting 8-bit data, then this transmission packet will be 10 bits because 8 bit is your data bit, 1 bit is your start bit, and another 1 bit is your stop bit. So our data range will be data width plus 1 down to 0, right? Means if your data width is 8, then your range will be 9 down to 0. Means total 10 number of bits, right? Okay, so I think we are done with our VHDL code for this UART underscore transmitter module. So we have this library declaration here. Then we have this entity declaration here, which is having three generic values, that is tx underscore data width, tx underscore system clock frequency, and tx underscore baud rate. And all of these generics are of integer data type, right? Then we have this port declaration. So these clock and reset are standard. Then we have this tx underscore start as an input type and steady logic. We have this tx underscore d in, that is input type, which is steady logic vector, and the range will be tx underscore data width minus 1 down to 0. Next we have this tx underscore dout, that is output type and steady underscore logic. And in the last we have this tx underscore ready, and that is again output type and std underscore logic. So that's complete our entity part. And now this is the time for architecture. So we have this architecture. Here we have declared both of our components, that is Baud clock generator and serializer. And we have also declared signals here, that is tx underscore Baud clock and tx underscore packet. Now the VHDL code is very simple. We have this first instance, that is Baud clock generator. So this is component Baud clock generator. So here first we have given the generic map. So this data width will be transmission data width plus 2. So we have two extra bits because one is start bit and another is stop bit. We have this system clock frequency, and that is transmitter system clock frequency. And this baud rate is your transmitter baud rate, right? Then we have this port mapping. So clock is connected to clock, reset is connected to reset. Now our start signal is connected to this transmitter start. We have connected our baud clock with the transmitter baud clock, and then ready is connected to this transmitter ready. So this is our Baud clock generator instance. And now we have this serializer instance. So this is straight again. Data width is tx data width plus 2, and default state is hard coded 1 here. Now port map. So clock is connected to clock. Reset is connected to reset. Now shift enable, which is our bit period according to the baud rate. So we have connected this shift enable to this tx underscore baud rate, and that will be generated from this Baud clock instance, right? And now this load input is connected to the tx underscore start. Our d in is our tx packet, and we have defined this tx packet here in this line, which is your start bit at the starting, which is your LSB, followed by your data bits, and then stop bit in the last, right? So this d in connected to this tx underscore packet, and our d out is our tx d out. Okay, so let's save this code, and now we will check the syntax for this UART underscore transmitter module. So for this we will open model sim simulator. So open it, model sim. Okay, so let's maximize this. Okay, so this is question mark. So let's compile it first. Compile all. Okay, so we have already created this project, and we already created this serializer and Baud clock generator in our previous sessions. And we have test benches for these two modules as well. And now we will import this UART underscore TX module we have just written here. And then we will compile this program to check if there is any syntax error or not. So simply right click, Now click on this add to project and click on existing file. Now click on browse. Now go to the source folder under this UART underscore project. So we have this source folder and this is the UART underscore tx.vsd file which we have just written. So I will select this file and I will click on this open button. Now click on OK. So you can see that this UART underscore tx.vsd file is listed here. So right click and now click on compile and then compile selected. Okay, so we have couple of errors here. So let's see that what are these. So just hover the mouse over these three errors and now double click on it. Okay, so let me make this little wide. So it is saying that every error is on this line number 62 and that is unknown identifier data width. So let's move to our VHDL code and look at this 62 line number. Okay, so this is our 62 line number. Okay, so it's right because this data width is actually tx underscore data width in this UART transmitter module, but we have used data width. Okay, so let's save this file once again and go to this model sim simulator. Now close this. Now select this UART underscore tx file, right click and then compile selected. Okay, so you can see that the compilation is completed and this is successful. And you can see the right tick here as well. Now we will write the test bench for this module and then we'll simulate it into the waveforms and we will see that functionally this is correct or not. So that was the VHDL code of our UART transmitter module and we have fixed all the syntax error in our code. But this does not mean that functionally it is correct, right? So now we will write a test bench to test this module and we will validate everything like reset condition, D in load, start bit transmission, data transmission, stop bit transmission, number of bits transmitted, bit period of our design, Baud clock calculation, etc. So subscribe us for the next update. If you did not subscribe till now, then please do subscribe to learn and grow community for regular updates. If this video is informative, then please like this video, comment on video, and don't forget to share. Thank you for watching.